So that was my first story about the Hubble legacy field. And I'm going to follow this theme about galaxy mergers and interactions for the rest of tonight. The second story is about this galaxy NGC 4485. And this was an image that was released by the Hubble people just to showcase a beautiful picture from the Hubble Space Telescope. And in this case, they're showing a spiral galaxy, and it's kind of hard to see the hints of the spiral shape because normally spiral galaxies we can see the spiral arms that are highlighted by dust or bright stars, and here you can't really see the spiral arms. But other astronomers in the past have imaged or looked at the gas in this galaxy, and by how it is moving, it's consistent with that of a spiral galaxy. But what's really interesting about this galaxy is that part of it looks normal, or what we think of should be normal, but the other half looks kind of crazy with all these stars and red nebulae popping out on the right side. This is kind of a two-faced galaxy, and it turns out that this Hubble image actually clips off the interacting galaxies. So this stuff that we're seeing here is due to this galaxy interacting with another galaxy, and in this case 4485 is interacting with this much larger galaxy 4490, and this galaxy is thought to be about 4 times the mass of 4485, and both of these had a close encounter, or the closest encounter occurred probably about 400 million years ago. And so these kind of encounters can take place over many billions of years. And the two galaxies, I believe, are slowly moving apart from each other. But what has happened is that you can see, again, those bright regions that we saw in the previous picture, and there are similar dots over here. And those are regions of intense star formation. And what has happened is that during this process where one galaxy passes the other, the tidal effects, basically the gravity of the two interacting galaxies, can compress some of the molecular gas. And that compressed molecular gas can instigate star formation. And so what we're seeing here are basically regions where in the dark molecular gas that where stars are born are basically too dark to see here. I mean, they're not being lit up by anything, so they're somewhat invisible. But what we do see are regions where these gas clouds have birthed many thousands, if not tens of thousands, of stars, and some of the stars happen to be massive OB stars, and those stars pump out huge amounts of ultraviolet radiation. They push out winds of stellar winds that can go out at 1,000 kilometers per second. And all that radiation and the wind pressure basically blows out a giant hot bubble of plasma. And so these red filaments that we're seeing are basically regions where these hot stars have evaporated the cold gas around them, and they've created this hot bubble of ionized gas. And then over time, the massive stars might blow up in supernovas, which can then disperse the gas completely. And so these regions here are the places where the stars are currently forming. But here you can see a bunch of bluish stars that are free of any of this red glowing gas. And so these are regions where supernovas have probably happened already, and they've basically pushed away the gas, and so you don't see any of that red glow anymore. And so these are just the massive stars left by themselves. And over time, all the massive stars will die out. They'll blow up into supernovas, and the most massive stars might blow up after only 1 million years. The least massive stars might take longer. They might take 10 million years to explode. But then over time, you won't have any of these massive bright blue stars anymore. Instead, the remaining stars will be the yellow stars, the red stars, which will live for many billions of years. So our sun is a yellow dwarf star, and the same region that's birthed hundreds or thousands of massive stars will have also created millions and hundreds of millions of the lower mass stars. And so those lower mass stars eventually enter into, they basically become part of the rest of the galaxy, and you can't really distinguish them anymore because they're not as bright as the massive stars. So let me just go through a cartoon picture of everything that I've described here. We have giant molecular clouds, which are these cold clouds where stars can form. And if part of a cloud starts forming stars, often what happens is you don't just form one star, but you form many stars. And some of these stars could be massive stars. So again, we have a handful of massive stars, and they have UV radiation and stellar winds, and they blow out this bubble of hot gas. And even the less massive stars, they can have outflows too that can push out and disrupt the cloud. So you can see the cloud here being disrupted or destroyed. And when some of these stars go supernova, they can create, again, a big expanding bubble. And what can happen is that the pressure from these supernova explosions can also induce further star formation, meaning they can press down on neighboring molecular clouds and cause them to collapse to form new stars. And so part of the reason that we might be seeing, while you have star formation here that was older and then star formation over here that's newer, is that this region down here, the supernova blew up a long time ago, tens of millions of years ago, and it instigated star formation further up in this picture. So this might be a region where star formation is propagated because of supernova going off. All right, so this is what observations show, but astronomers have, there are actually different types of astronomers. There are astronomers who go and use telescopes to take observations, but there are also a second class of astronomers who theoretically apply physics to try and understand how and to explain the phenomena that we see through our telescopes. And then a subset of the theorists are the ones who use computer simulations to further simulate these phenomena. And so what we'll see, I'm going to show a few videos of one of these simulation groups. And what we're going to see is basically how galaxies form from the Big Bang forward to the present. So what we're going to see now is a simulation of gas after the Big Bang. And what is happening here is the gas is collapsing inwards entirely due to gravity. So gravity at cosmological scales is the most important force. And as the gas collapses inwards, they pile up to form galaxies, and those galaxies have stars. So we're not seeing the stars here, we're only seeing the gas. And the colors represent different temperatures of gas. So this light green is relatively cool or warm gas. The red is hot gas. And what happens is there's a spiral galaxy. You can even see a hint of the spiral shape here. Cold gas is falling in, and that gas, as it falls in, it can compress, form stars. The massive stars blow up in supernova, and the supernova propels out extremely hot million-degree gas. So the reason why we have lots of red, extremely hot gas out here is because of the supernova. And you can even see that some of these explosive events are so propulsive that they send out colder gas out, and then they fall back in. And so this is a simulation of how a Milky Way-like galaxy, a disk galaxy, can form. And this is part of a team called FIRE, Feedback in Realistic Environments. And it's a team of astronomers at multiple universities, institutions around the country. And here we have another spiral galaxy that's forming. And it's about to now merge with and collide with this. And you can see that the merger can take multiple orbits, meaning it passes through and then it'll fall back down. So it doesn't merge right away, but it takes multiple free falls for it to merge. There's a question?
Yeah, when you talk about like the original galaxy forming because of gravity, what's creating that gravity? What's the massive thing?
Yeah, what's creating that gravity? That's a really good question. It turns out that at large enough scales, we think that That's actually one of the big mysteries that astronomers haven't quite resolved yet. Meaning, if you look at what happens immediately after the Big Bang, we expect the universe to be so smooth, meaning the gas isn't crumpled up or collected in certain spots. It's just uniformly distributed. And there's actually some problems in trying to get that extremely smooth gas after the Big Bang to start collecting due to gravity at a rate that would make sense for us to see galaxies 13.7 billion years later. So there are proposals about what could cause irregularities in the smoothness of that gas, but it's not something that I have time to talk about, so you're welcome to come and talk to me afterwards, after the presentation tonight. But that's a really good question. All right, so here is another simulation from that same team, but now instead of looking just at the gas, we're looking at the stars. So this is a Milky Way-like galaxy, and it's merging with a Magellanic Cloud-like satellite galaxy. And so in this case, not only are they showing the stars, but they're realistically showing what the molecular clouds would look like. That's the dark regions. So those are the dark clouds where stars can form. And so again, we're looking at many billions, hundreds of millions to many billions of years worth of time. And so these simulations are getting better and better. And when I first saw these, I mean, I was just blown away by how amazing these simulations are. And you can see that at the end of the simulations, large tidal tails of stars get stretched out. And that's just due, again, entirely to gravity in this situation. And we know that our Milky Way has a big halo of stars that aren't collected in the disk, but they orbit in a region, out, from the disk all the way out to many times the distance of the disk. And we think this halo is due to multiple merger events that the Milky Way has suffered through its history. And the other really amazing things about these simulations is that they can create simulated galaxies. So here are just a sample of simulated galaxies that I downloaded from the FIRE website. And what's amazing about this is that they look very much like galaxies that you would find from the Hubble Space Telescope. And so here are just a bunch of spiral galaxies that were completely simulated. And you can tell that the star clusters out at the edges are kind of marbly. But the molecular clouds look really good. So these are really amazing simulations. And then here is a compilation of multiple galaxies that they've simulated. So you can see that each of these has names like Romeo and Juliet and Thelma and Louise and Batman. The color, the red and green represent the gas, and then the black and white represent the stars. And so they're basically running simulations using supercomputers showing how you can generate galaxies that could look like galaxies today. And so in these simulations, astronomers run these simulations not just to run them, but what they hope to do is to compare them to observations to show whether the model parameters that they put in can create structures, can create galaxies, can create hierarchical clustering that matches what we observe out in the real universe. And so by tweaking or changing the parameters of these simulations, they can change things and see if they can match what we observe. And of course, what goes into these simulations are our best ideas about what is in galaxies and how the physics of galaxies play out when you have star formation taking place, when you have supernovae going off, and we have gas getting ejected out. And of course, you have different populations of gases at different temperatures, and you have lots of different types of stars in here. So these simulations are extremely complicated.